to carry on the discussion of the VSEPR model or prediction of lowest structures and therefore orbital shapes or molecular shapes. This time we take another case where the number of electron pairs is 4. So it's the VS again, the VSEPR model. It's a 4 electron pair case. But this case is actually different from the one that we have discussed before. Not all electron pairs are bonding. So let's say 3 bonding, 1 non-bonding. And a typical example in this case would be ammonia. So this is ammonia. This is the formula of ammonia, where nitrogen makes 3 bonds with the surrounding hydrogen atoms. And again, in order to draw a possible lowest structure, we need first to calculate the total number of valence electrons. And the total number of valence electrons would be 5 from nitrogen. Remember, nitrogen is located in group 5A, so 5 valence electrons, plus 1 from each of these hydrogen atoms, so the total will be 8 electrons. 8 electrons, if you divide that 8 number by 2, you get the number of electron pairs that should be present in a possible lowest structure of ammonia. So if we divide 8 by 2, we get 4 electron pairs. Now to draw a lowest structure, we always draw the central atom, which is nitrogen. Okay, so that's nitrogen. And the surrounding hydrogen atoms, so that's 1, that's 2, and that's 3. The next step is to draw a line, a bond basically, between the central atom and the surrounding hydrogen atom. So that's 1, 2, 3. And if you calculate the number of valence electrons so far used in this structure, you would find that there are actually 6, but we had 8. So we have 2 to go. If you look at hydrogen, it has obeyed the duet rule because each of these hydrogen atoms are surrounded by 2 electrons. So that's according to valency rules. In this case, of course, specifically according to the duet rule. But if you look at the central nitrogen atom, you will see that it's only surrounded by 6 electrons, and that's not satisfactory because we know that nitrogen is in period 2. It should obey the octet rule. In other words, it should be surrounded by 8 electrons. So there are now 6. That additional pair should be in the form of a lone pair. So that's the lone pair. And this is now good, satisfactory, because nitrogen is now surrounded by 8 electrons. If you calculate, again, the number of valence electrons in this structure, you would find 2 and 2 and 2, that's 6 plus 2, that's 8. And we had 8 before, so that's good. If you look at the electron pairs that we had before, we had 4, and now we have 1, 2, 3, and a lone pair, so that's 4. So this is also reasonable. What we need to look at right now is the orbital shape or the overall arrangement of electron pairs, followed by a prediction of molecular shape, accordingly taking into account the lone pairs. So let's try to predict the arrangement of electron pairs. And since there are 4 of them, so the orbital shape, just like methane, is actually tetrahedral. The arrangement of electron pairs, in this case of ammonia, or the orbital shape, is also tetrahedral. So let's write that down. So that's tetrahedral. But the molecular shape, however, okay, may not be tetrahedral because now there is a lone pair. So we can actually represent that by taking one of these bonds off. Now, so that's basically like the lone pair. If you look at this molecular shape, you will find out it's no more tetrahedral. If you look at this shape, it's like the shape of a pyramid, okay, but triangular. So this is triangular pyramidal or trigonal pyramidal. So the molecular shape in this case of ammonia, and in all cases when there are 4 electron pairs and one of them is a lone pair, is trigonal pyramidal. So the molecular shape is trigonal pyramidal or triangular pyramidal. Now, what about bond angles? Well, clearly the bond angles will not be exactly 109.5, and that's because of the presence of a lone pair. Now, lone pairs occupy space. And remember, this model, the VSEPR model, is based on minimization of electron pair repulsions. We are talking about bonding repulsions, bonding non-bonding repulsions, and non-bonding repulsions. Now, that lone pair around the central nitrogen atom occupies space, and because of that, the bonds, each of these hydrogen bonds will try to squeeze a little. They will shrink a little, if you like. Okay, therefore, the bond angle in the case of ammonia will actually be less than 109.5. It is found, in fact, experimentally to be 107. So the bond angle scientifically or accurately represented to be less than 109.5, and that's to account for the lone pair, that lone pair which occupies space, and the idea is to minimize electron pair repulsions. Now, to conclude, ammonia is an example of electron pair case where 3 of them are bonding, 1 of them is non-bonding. The orbital shape or the arrangement of electron pairs is tetrahedral, whereas the molecular shape is trigonal pyramidal. The bond angle in the case of ammonia is scientifically represented as to be less than 109.5, and that's because of the presence of a lone pair.